Okay, so potentially hi to YouTube. Good to see you out there. We'll wait for the word that YouTube is actually streaming from Megan. Let's see. I think that's probably looking good. All right, welcome YouTube. Welcome everyone. Let's go to this. All right, so welcome everyone. This is the last Water, Wetlands, and Watershed seminar of fall 2025. And we're very lucky today to have Dr. Eric Stein with us. So Eric, you get the award for the furthest distance traveled for this seminar. Excuse this box, and so this is some swag from both the Center for Wetlands and the Center for Coastal Solutions, and hopefully, yeah,
So don't forget it.
yeah. So Dr. Stein is the head of the biology department at the Southern California Coastal Water Research Project, which they just call SWRP. The C's are silent, and he oversees a variety of projects about bioassessment, coastal wetland water quality, what we call minimum flows and levels here in Florida, but things like environmental flows, how much water does the river need for its ecological function versus things like recreation, which you might argue is in a sense an ecological function. His research focuses on human activities and basically the status of aquatic ecosystems. He's authored over 150 journal articles, 80 technical reports, 3 book chapters, and he just is cycling off as the president of the Society for Wetland Scientists. Before joining SWRP, he served 6 years as a senior project manager at the Los Angeles District Corps of Engineers, so working for the feds in a regulatory role, and then 4 years with a private consulting firm. So Eric, thanks so much for coming. The floor is yours.
Thank
I
you.
think this should work.
Yep.
If not, click back on the screen.
Super. Thank you so much. And I'm thrilled to be here. I got a little bit of background on the history of this series, so I'm really feel honored to be here. And so you can see the title of my talk about the eco-hydrology tools from California. There's my QR code if you want to reach me, but really this is what it's about, right? Like this is the question we're all struggling with, like how much water should we leave in these systems for the fish or other critters, right? And so that's what I'm going to talk about today. But before I do that, I'm going to tell you a little bit about the agency I work for because it's a little bit of a unique place to work, and I find people are kind of interested with the model of our organization. And it's also important because it provides a context for sort of some of the work that we do. I'm going to give you a little bit of background on California water issues because they're quite different than Florida water issues. And so that's also important context for the motivation for this work. Talk about the statewide environmental flows framework that we've developed, and then give you a few examples of how it's being applied and some of the technical tools. So these are my key takeaways, right? Because I'm going to cover a lot in the next 40 minutes or so, but if you sort of take nothing else away, hopefully what I'll impress upon you is that these are complex issues. We work in complex environments. You need sort of a whole toolbox, right? There's no one solution that's going to fit everything. And so we've gravitated towards a risk-based approach, and I'll talk a lot about that. It's, I think, more gratifying as a scientist, less gratifying as a resource manager who has to implement it, but I think there's some distinct advantages. And then the other thing I'll try to sprinkle on through here is that pretty much everything that we do has been a co-development process. We work closely with the implementing agencies and the affected parties from project inception. That's really important because these are complicated issues and there are no clear-cut answers. And so working this co-development process is really important. Those are my key takeaways. So let me tell you a little bit about my agency. We're what's called a joint powers agency. So if you're not familiar with JPAs, a joint powers agency is when a bunch of other agencies come together and form a regional entity to do some sort of common mission. There's lots of different joint powers. They can do transportation, they can do wastewater. Our joint powers was formed in 1969. Motivated by the State Port of Cologne Act, which is California's Clean Water Act. And our joint powers is a little bit interesting. Our mission is really basic research related to water quality and aquatic ecosystem health. But what makes our JPA really interesting is that we have some federal agencies, some state agencies, and some local municipalities. And about half our agencies are regulatory agencies, state and federal regulators. The other half are dischargers, wastewater and stormwater agencies. So we kind of sit between the regulators and the dischargers. And our mission is to sort of do the science with the collective so that we're kind of working on it together. They may not agree on the policy, but hopefully we're doing the science together. So we sort of form this kind of regional scientific hub. And people often ask me, I'll tell a little bit about the funding. People sort of ask, so about 25% of our money comes through direct funding from our 14-member agencies. The other 75% is contracts and grants and competitive money, just like everybody else in this room has to. So it's sort of a 25-75 mix. These are our technical departments. I head up the biology department, but we do lots of other things across the agency. And so we do everything from fundamental research to we administer large regional monitoring programs. Our oldest regional monitoring program goes back to 1994. And so we administer these ongoing regional monitoring programs together in excess of 100 different organizations to collaborate on regional monitoring. And a lot of it is, again, we do a lot of the science to policy translation. So working directly to integrate the science into policy. We have a number of research areas. Each one of these has sort of a research vision associated with it. They evolve and change over time, but most of what I'm going to talk about today falls into our ecohydrology with a little bit of touch onto some of our bioassessment. But these are our current 8 research kind of focal areas. All right, so that's a little bit about SCORP and where I work. It's an interesting and really cool place to work. I'm a huge baseball fanatic, so I sprinkle in, I love Yogi Berra and all his quotes. But I wanted to tell you a little bit about hydrology and why it's important to really observe these things over long periods of time, because it's a really complicated place to work. So this is a really pivotal paper Mike Dettinger published this in 2011. And so what this map shows is it shows the coefficient of variation of annual precipitation across the country. So you can see down here in Florida where we are now, and if you look at California, those colors mean higher coefficient of variation. So it's a highly variable environment. Pretty, very distinct from anywhere else in the country in terms of the variability at a continental scale and then within the state itself. And so as a consequence of that precipitation variability, we have lots of variability in runoff. So this is the San Joaquin, this is the central kind of main delta area of the state of California. What this graph is just showing over about a 100-year period, you can see runoff varies from these really wet years. We have these really wet cycles and really dry cycles and critically dry cycles. And it's highly variable over time, right? So we're dealing with this very sort of unpredictable, somewhat stochastic environment. And so this is Lake Oroville, our second largest water storage reservoir in the state. And so it can look like that in 2014. And in 2011, 3 years before, it looked like that, right? Same bridge. And so we go through these massive sort of boom and bust cycles in our water resources. And so because of that, groundwater is a really important component. People don't often think about groundwater in California, but it's a really critical component. And with this graph, the lighter teal bars are showing the proportion of water that comes from groundwater on an annual basis in different regions of the state. We have over 500 groundwater basins. And until recently, groundwater was not regulated in the state. And so when we have these drought periods, people just suck all, that's what they turn to as to make up during those extended dry periods. So as a consequence, we have things like this. This is a colleague from USGS showing the amount of subsidence between 1988 and 2016 associated with groundwater withdrawal. So big issue. And so in 2014, the state passed something called the Sustainable Groundwater Management Act, or SGMA. And that was the first time in the history of the state that groundwater has been regulated. Of course, like all good regulations, it was passed in 2014. It took about 10 years to be fully implemented. So we're just now starting to see the first permutations of groundwater management in the state. And a big part of groundwater management is consideration of the impacts of groundwater withdrawal on groundwater dependent ecosystems and groundwater supported base flows. And so that drives a lot of what we do in the ecohydrology program. The other thing that's important to know about California is this map over here on my left basically shows the annual runoff. And so even within the state, we have these really wet up in the north. It's like, very high precipitation. Down where I am in the south, very low precipitation. So huge variability in the amount of precipitation patterns in the state. And if you look at the population centers in red, like down in Los Angeles, there's a mismatch between where the water is and where the people are, right? And so as a consequence, we move a lot of water around the state. There's over 700 miles of canals. And I looked up the numbers, something like 12 million acre feet of water is moved every year around the state. So a lot of water. And so that's a very California thing. This is the California aqueduct. This one here is right. This is the famous William Mulholland stood right here and said, "There, take it." This is where the water comes up the last rise into northern Los Angeles. And so what this map shows is we bring water from the Owens Valley. We bring water where the city of Los Angeles actually owns all of this water. And so they bring that down from Owens Valley. We bring water from the Delta down. We bring water from the Colorado River, right? So a lot of water movement around the state. But because we go through these big boom and bust cycles, and we all know the Colorado River is becoming even, harder to manage over time, our municipalities are really trying to think differently about water resources. And so what this graph shows, this is from the San Diego region, that in 1991, this yellow part of the pie chart shows that 95% of the water for the region was imported to the region, right? And so over time, the municipalities are trying to diversify the water portfolio to have a much more, so the goal by 2035 is to have only 2% of it be imported. And the thing that I want to point out is this purple, this potable reuse. This is really reuse of treated wastewater and reuse and stormwater capture. So there's a lot more attention and money being put into these uses. Just as for context, in the San Diego region alone, we discharge about 350 million gallons a day of treated effluent. And so that is a big effluent, and that's just in San Diego. Los Angeles is another 350, Orange County another 300.
To the ocean.
To the ocean, right? So there's a lot of interest in reusing that water as much as possible. So as a consequence, all of these water uses like irrigation return flows, stormwater retention, use of treated wastewater, groundwater, we're rethinking all of those. And so the fact that we're rethinking all of those causes us to really think a lot about this balance, right? Because a lot of that water, which traditionally would have gone into streams or into estuaries or things like that, is now being diverted for reuse purposes, right? And so we have a lot of policies in California that have evolved over a handful of years to try to figure out, like, how do we deal with balancing water use with all of these different competing uses and kind of the shifting landscape of how we use water in the state. So we have everything from the salmon strategy in the North Coast, right? We have a very important anadromous fisheries, which are highly imperiled. We have the water action plan. We have the water resilience and recycle policies, which really talk about how we want to reuse water. I talked a little bit about SIGMA. And then the big driver lately is this one, the cannabis cultivation policy, which really drives a lot of work because a lot of the cannabis growers, now that it's legal, draw water off streams, and part of that policy has to do with making sure that those withdrawals are not causing adverse environmental impacts. So all of these policies, and this won't surprise any of you, which all are administered differently by different agencies in different parts of government with virtually no coordination or interaction, are trying to answer the questions of, like, how much water should be left in the streams, how much groundwater should we pump, how much should we capture in stormwater, and how much wastewater. So these are all happening somewhat in kind of silos in different parts of the state. But they're all trying to answer this fundamental question, right? They all have the same underlying question, which is, how can we establish environmental flow targets that are broadly protective of stream ecology while still allowing for these other demands? But they're all sort of historically trying to get at that in very different ways. So, but don't despair, right? It's a very complicated, lots of agencies, lots of questions, lots of silos, because science comes to the rescue. Right? So hopefully many of you know who this person is, one of my favorite scientists.
Do you all know who that is?
You guys know who that is?
Dr. Brent.
Doc
Thank you.
Brown, yeah.
Good.
All right, so about the 2015 timeframe, largely motivated by the cannabis program when that policy was being enacted, a group of us came together to produce the California Environmental Flows Framework. And the goal of this was to bring together large groups. You can see we have a large technical team, which involves universities, some NGOs, which are really important partners like Trout Unlimited and CalTrout, some agencies like USGS. We've sort of worked collectively to say, can we develop a framework? So this is not a model, but it's a framework and approach for how to kind of work through this process of trying to set flow targets that achieve that goal in the slide a couple of slides ago. And it's the first version was published in 2021, and it's currently being implemented in a variety of ways across the state. And I'll give you a few examples of that. And so people ask me, like, what's sort of the most impactful thing about the California Environmental Flows Framework, or CEFF? And I always tell them the same thing. It's the fact that we actually got multiple agencies together to agree to do something in a similar way and have comparable methods. So that's the science is cool and interesting, but the fact that we got the agencies to actually talk to each other and work together is probably, in my opinion, one of the bigger accomplishments of this effort. And so the goal, you can read a lot about CEFF at the URL, but really is trying to help avoid these train wrecks, right, between these different competing uses. So CEFF is sort of founded on this idea of functional flows. This was originally published by my colleague Sarah Yarnell at Davis. And so what functional flows are is we think about the annual hydrograph and we're trying to move away from this idea of minimum base flows or dry season base flows. And we try to think about the hydrograph holistically because our goal is not just to protect one target species like an anadromous fish, but really to protect the whole ecology of the system. So the idea is if we probably can't replicate the historical hydrograph because there's been so much manipulation on the landscape. But we can think about these 5 key components of the annual hydrograph: wet season base flow, peak flows, spring recession, dry season, etc. And if you think about these 5 components of the annual hydrograph, and if we try to manage flows within certain ranges and we try to replicate enough flows within each of these 5 components, we can support enough of the function of the ecosystem to support a broad suite of the entire ecology of the system. So we're not trying to replicate the hydrograph, but really just manage within these 5 components and replicate enough components of the hydrograph so that we can hopefully get some ecological support there. So operationally, the way we do that is this is that same different depiction. And we sort of think about different portions of the floodplain that are accessed and engaged functionally through those different 5 components. And then we can take those 5 functional flow components and we can translate them to different metrics. So for each of these 5 components, we have a series of metrics that relate to magnitude, time, and duration, sometimes rate of change or frequency. And we have actual numeric ranges associated with those boxes that I showed you. We can set numerical ranges. And so we have 24 metrics, and some of them are more important in some areas than others. But we can now set sort of quantitative ranges for each of those 24 metrics for people to start to aim for from a management perspective. So that's kind of the concept of CEFF and sort of the framework for how we're starting to think about managing environmental flows. So we've developed a whole bunch of tools through that website. We have R scripts. You can put flow time series from a model or from gauge data, et cetera. And so we've developed a whole toolbox to help people implement them. But one of the fundamental tools that's sort of foundational is the whole concept of these functional flows is you have to understand something about the natural hydrology of the system. And so when we started this project, the State Water Board, which funds a lot of this work, said, we don't have enough time or money to model every basin in the entire state of California. So we need something that provides some foundation of understanding what are baseline conditions that we can compare against when we're thinking about alteration. So we partnered with USGS, Darren Carlisle in his lab in Lawrence, Kansas, and Darren and his collaborators developed a model. This is a statistical model. It's a nested random forest model. And basically what they tried to do is say, can we estimate not what the hydrograph is, but those 24 metrics, can we statistically predict what those 24 metrics would be under natural conditions for every NHD reach in the state? So that was the goal. So Darren labored away at this for a few years. We would talk to him in Kansas. He'd say, my server is heating up the entire city of Lawrence right now. But what it produced was this web tool. This is Rivers, a Code for Nature. It's hosted by the Nature Conservancy. And so you can now go into any NHD reach in the state of California. You can pull up whatever of those 5 flow components. You can look at the flow metrics, and then you can look at it at different water years, wet years, dry years, moderate years. And you can at least get some ranges of what kind of those baseline conditions are. So we have a foundation. Now, if you have a watershed specific model, by all means, that's going to give you a better precision. But if you don't, for many parts of the state, you can at least go to any NHD reach and you can get some estimation of what those kind of fundamental baseline hydrologic conditions are and what that quote natural conditions would be. So that's a really important foundational starting piece for using this entire environmental flows framework. And so this is kind of the USGS open file report that kind of was the foundation of that work. It's all available online. So now we can go to any place in the state and we can get some sense of what the natural hydrograph should look like under natural conditions based on the landscape setting of that reach, right? So remember, this is a statistical model, not a deterministic model. And so then what we're trying to understand is what is the acceptable degree of departure in that hydrograph, and when do we get to a point where we're at an unacceptable degree of departure? And what we're actually trying to then do is then put these into risk categories conceptually, right? So we can sort of tell a manager at certain levels, you know, if you have this amount of departure, you're sort of at a good, so moderate risk. And then a manager can decide sort of how risk tolerant or risk averse they might be in their management decision, given the other demands on the system. So again, our job as scientists is not to give them the answers, give them the tools to make an informed decision, right? And so we take that type of conceptual hydrograph and then we translate it to this regional risk curve. And so the idea conceptually is we're going to say how much, if you start at 100% of unimpaired flow, so this is natural, and as we decrease flows, what is the associated ecological risk? So more altered, as you move away from those unimpaired, those natural flows, get higher risk. And then so we want to basically be able to convert that to different risk categories so that a manager can come along and say, where do I want to be in terms of my desired risk level? So that's the concept behind what we're trying to develop for the management community. And so this is the process we use and how to operationally do this. We always start with the management goals, right? So we always have to say, what are you actually trying to support? Is it broad ecology? Is it certain threatened and endangered species? Do you have recreational uses that are important? Do you have consumptive uses that are important? And so then we can develop these flow ecological relationships based on the management goals. We can go through this process of thinking about different degrees of altered flow. We develop these eco-risk relationships, and then we ultimately get to that risk-based curve that a manager can use. So I'm going to kind of step you through a little more detail how we go about doing that. So that we use sort of, I mentioned that we use a toolbox approach. So we do, some of it is based just on hydrology. Some of it the second level we often do is this, we use our traditional biointegrity indices. So these are our routine bioassessment indicators that we use all over the state of California based on benthic invertebrates and algae. We've got a wealth of data. The state of California has been doing this for a long time. We've got well over 5,000 monitoring locations in the state. And this is a good measure of overall ecological condition, right? We like biology because it integrates what's happening in the environment over time. And it's a good sort of integrative indicator of general ecological health. A lot of times we stop there, but in many cases, because we have lots of sensitive species, we go to this third level where we have specific threatened and endangered species or species of management concern, and we need to get a little bit more precise on the needs of those species. So I'll give you some examples of each of those. So starting with functional flow metrics, remember our goal is to think about as we deviate from this unimpaired time series. So what we can do with our models is we can take this unimpaired time series and we can start to then model the changes in the hydrograph at 5% intervals. So we just incrementally sort of model or simulate removal of or diversion of the flows or alteration of the flows at 5% intervals. And then using those functional flow calculators that I showed you, we can then say if this is the range of this is one of those 24 metrics, this is dry season base flow, so one of those 24 metrics. And I can basically say, what's the range of that dry season base flow at unimpaired over the period of record that I'm modeling it. And then as I incrementally step down, I can see how the range of that metric is sort of changing over time as I incrementally reduce the flows. And so that I can take that and I can convert that series of box plots. And if this is just showing the median, so all I did here is plot the median value. And I can go to manager and say, maybe you want the upper quartile, the 75th percentile. This is median, but again, that's a management decision. So now I can look at this. And so I have, at least from a purely hydrological perspective, I have a relationship between the deviation from unimpaired flow and this type of risk, which is just a delta base flow. So the change in base flow is a reflection of risk associated with the deviation. So I can start to sort of quantify hydrologically that risk relationship. So operationally, these are just a couple of examples of how that purely hydrologic assessment has been applied. This is a project we worked on in Southern California in the San Juan Creek watershed. We just applied that and said, if you look at the current conditions relative to those natural conditions, and you say that more deviation from natural is higher risk, we can start to map throughout the watershed areas that are lower risk and areas that are in higher risk. And the local municipality then, the county, in this case, uses this map to target where they're going to do flow remediation. So in areas that are higher risk, they'll target their limited resources in those areas because those are the high risk areas. This is an example where California Department of Fish and Wildlife is setting in stream. They set in stream flow hydrographs for certain watersheds where they have species of concern. And so they took those 24 functional flow metrics and they kind of stitched them together into a synthetic annual hydrograph for wet years, moderate years, and dry years. And then they can tell the managers, if you kind of try to simulate, get as close as possible to this blue line, that's what we want you to aim for in sort of your water management, depending on whether it's a wet or moderate or dry year. So these are just examples of how, just from a hydrologic perspective, you can take those flow metrics and then translate them to something that is used in a management context. And so that's agnostic in some ways to biology. It's just sort of making the assumption that if you protect the hydrology, that you're going to protect the biology. But we often want to go to this next step, which is sort of thinking about these general indicators of ecological health. So in California, we have standard bioassessment indices that, like many places in the country, ours is called the California Stream Condition Index, or the CSCI. We have one for algae that's called the Algal Stream Condition Index, or the ASCI. And they all sort of work the same way. If you're not familiar with bioassessment indices, this is what we call a predictive O/E model. And so basically what we do is we go out, we have about 5,000 sites across the state. We have about 650 reference sites. So we can pull all the bioassessment data from those reference sites, and using basically another random forest model, we can relate landscape characteristics to the benthic community. So we can create a prediction that says, based on the landscape setting that you're in, what type of benthic composition should we see in that stream if it were not impacted? So that creates an expectation. And then we can go out and measure, we can do our traditional kick net sampling and collect the bugs and do the enumeration. And then basically you can generate your normal set of bioassessment metrics. These are pretty standard bioassessment metrics. These are functional metrics of the community. And we can see what we see, what do we see in the actual field observation relative to what the model says we should see under natural conditions based on those 650 reference sites. So we just do an O/E for each of these metrics, and then we average them up, and you usually get a score from 0 to 1, and that's sort of our bioassessment score. But the goal is we need to set a target, right? Because we're trying to understand like how much deviation is too much deviation. So the way we've done it to date is we look at the reference distribution, that those 650 reference sites. We take the 10th percentile of that reference distribution. So we look at the scores of those reference sites. We take the 10th percentile of that reference distribution, and that's 0.79 on a 0 to 1 scale. So that's our definition of good now. So basically, for a site to be considered good or good quality, it has to be at or above the 10th percentile of the reference distribution for the benthic community. So that's kind of now our key number, right? That says good versus bad, our threshold. So now what we can say is, how do you relate those functional flow metrics to whether or not the stream is in good or bad condition based on the bioassessment, based on what the biology is telling us? So we have 24 metrics. We want to know which ones are the most important because we want to constrain the analysis in a little bit more of a reasonable way. So this is a boosted regression tree analysis, and it's really just asking which of those 24 functional flow metrics are most associated with changes in the biological community. So which are the most predictive of those biological changes. So we have a set that are really important for the bugs and a slightly different set that are important for the algae. So now we can take those 24 metrics and we can kind of narrow them down for the ones that are most associated with responses in the biological community. And then we take those and we focus on those metrics, and we use a GLN. This is just a simple logistic regression analysis. And what we're doing is we're looking at sites that are sort of in good or bad condition from the bioassessment perspective. And then we're looking at the ranges of those, what are the flows like. We look at those 24, those key flow metrics, the ones I showed you back here. We look at the ones in yellow. So we look at those flow metrics at sites that are in good bioassessment, so above 0.79, and sites that are in bad bioassessment, below 0.79. And then we can do a logistic regression analysis and understand the relationship between changes in those hydrologic metrics, which is on the x-axis. So the changes, in this case, this is dry season base flow again. So how does dry season base flow? And the way logistic regression works is you get a probability. So we get the probability of being above or below that sort of good level, the probability of being above or below that 0.79. And so you'll notice it's a two-tailed, right? Because you have a different model for a negative in the negative direction, so a decrease in the base flow, and a different model for an increase in the base flow, because the bug community can respond to both increases and decreases in the base flow. And so again, we can talk to a manager and say, what's your risk threshold? In this case, I'm showing you 50%. That's not magic, right? You could decide that maybe I want a 75% probability of having good, but in this case, for example, we're using 50. And so at that point, I can now say, how much dry season base flow can I accommodate and still be having a 50% probability of having that good bioassessment score. So now I can set a range of base flow. So if I don't decrease my base flow by 3 CFS or increase it by 10 CFS, if I stay in that range, I know I have a 50% probability of being in good biological
And
conditions.
that's delta of the magnitude, not the percentage, right?
Right,
It's a
yeah.
small number of CFS.
Exactly.
Reminds me of the intertecting gauge.
Yes,
Yeah.
yes,
Yeah.
it is a small number of CFS. But again, a lot of these, this is done in Southern California. I mean, base flow is often in that range.
Yeah.
So that's kind of in a nutshell. So we do that over and over, and we have a series of metrics. I showed you dry season base flow, but we can look at other seasonal metrics so we can get a sense of what's the risk during the wet season versus the dry season. Turns out the benthic communities often are very responsive to those wet season base flows as well. All right, so that's kind of the first and second levels, and that's what we routinely do. But it turns out we actually have a lot of sensitive species in California. Right? It's often considered a biodiversity hotspot. So we have lots of anadromous fishes, like the steelhead. We have sort of native cold water fishes, like the Santa Ana sucker, small little native fish that are highly endangered. And then today, I'm actually going to give you an example with the arroyo toad, which is, I think, how we started talking about this native, basically because of the work we did on the arroyo toad. So I'll give you an example of how we now go from that general biology to sort of a specific species using the arroyo toad as an example. And so basically the way we're trying to take this risk-based approach. So we actually had a lot of conversations for like, how do you actually enumerate or quantify this? And so after kind of going back and forth and trying a bunch of things, we basically decided that we're going to quantify risk based on this concept of thinking about the number of days that the stream has the flows that are necessary to support a key life stage under unimpacted conditions. And as you get less days, right? So as you decrease the number of days that suitable hydrologic conditions occur, that's going to be how we're going to sort of quantify or communicate risk. So I'll kind of walk you through that, but that's kind of our fundamental premise. So let me introduce you to the arroyo toad. Super cute, right? If you love amphibians. This is one of our native ronids, or native toads. Small, you can see 5 to 8 centimeters, right? So it's a very small endemic species. It's both federally and state listed. It's obviously a lot of direct habitat loss, like a lot of areas. But one of the major threats to this is hydrologic alteration in 2 ways. This toad breeds in these small marginal pools along the margins of the floodplain. And so engaging those small marginal pools is really important. But when you amplify flows, or so you start to increase these small little base flows, then we get invasive bullfrogs come in, and they're highly predatory on these species because this is a very small species. So flow is a really critical factor to the life history of this particular species. So we actually address this in a couple of ways. We use some species distribution models, which tell us something about where is the species likely to occur based on the physical conditions. And then we use a species response model, which relates some sort of hydraulic parameter like depth to some sort of ecological response. So we're coupling a species distribution model with a species response model. So the species distribution model, we started with a model, Mike Treglia from USGS had produced a species distribution model for this species that was based purely on landscape characteristics. So again, this is just a random forest analysis looking based on these landscape characteristics. So we basically took Mike's model and then we added in the functional flow metrics and said if we couple landscape characteristics with these functional flow characteristics, can give us a little bit more ability to predict where the species is going to occur. And that was the paper that Katie Irving, who works with me, published it earlier this year. And so it turns out when you look at the variable ranking that comes out of this, that the flow characteristics, so this plot is just a variable ranking, so it shows you as the model decreases in accuracy, which of the parameters, which of the variables in this random forest model are most associated with the predictive accuracy of the model. And so it turns out that a lot of these flow metrics are pretty important relative to the landscape metrics, which are some of the landscape metrics are down here. A lot of these flow metrics, not surprisingly, are really predictive or really important to the accuracy of the model. So we're able to identify that we have these peak flow magnitudes, spring recession flow, and dry season base flow. Those are really predictive or important to be able to predict the occurrence of this species. And if you think about it in first principles and how it relates to the ecology of the species, it tends to make sense. So we applied all that, we went back through, and then we were able to produce this map, which now actually gives us some estimation of where within this region where the toad tends to occur, where in the warmer colors, where we have a higher probability of seeing the toad occur based on the sort of flow and physical condition, the landscape conditions. We can sort of understand where we should likely see this. And this is the paper that Katie published on this. And then the fun part is we can do things like take future climatic and say under different climatic scenarios, and as we change some of these physical parameters, how do we expect the distribution of the species to change? And so from a management perspective, you can think about either I want to maybe protect areas or I want to remediate other stressors in those areas because I know those are going to be more at risk in the future under future climate conditions. So that's a way you can use the species distribution model. But as my old friend Yogi Berra says, that really doesn't help you if you're a manager. And this is probably of all my Yogi Berra quotes, my favorite Yogi Berra quote. Because in practice, we still need to make a management decision, right? And so being able to predict climate futures is interesting, but it doesn't help you make a prediction. So the way we want to try to make this prediction is we take these, basically this is a very habitat suitability index. It's a very classically used method, right? Where we have data that has been collected and models. These have often been developed over years. A lot of them are published. We have a certain hydraulic parameter, like in this case, depth or velocity. And we can get a habitat suitability index that's related to the range of these hydraulic parameters. And there are lots of these that are published, right? It's a very commonly used method. And so in this case, we picked, again, a certain measure, 8.8, right? Again, nothing magic about that, but we said we wanted 80%. We want to be at the 80th percentile. We're trying to be protective. So we can use that habitat suitability index. We can couple that with model hydraulic and geomorphic models, which are really important. Because remember, I told you this toad, the marginal pools are really important. So we need to know something about the morphology of the stream and the hydraulics associated with that morphology. And so we have what's called a river builder model. This was developed by Greg Pasternak at UC Davis. So we have a river builder model that tells us something about the morphology. We can couple that with a standard hydraulic model like HEC-RAS. And then we can produce a curve that looks like this. Because managers are not going to manage depth and velocity, right? You can't manage depth and velocity by turning a knob very well, right? Maybe velocity, but it's what they really want to manage is flow, right? That's what they're measuring. So this model coupling allows us to take this habitat suitability index, and then we can convert that to sort of the amount of habitat area that's supported under different flow rates. So again, we want to target this 80%, nothing magic, but we want to be up in this protective area. So now we can think about what flow range is associated with being able to be in this high habitat quality. So we can relate flow to the amount of habitat quality. So then remember I told you we take this days approach. So now we have this relationship that relates flow to habitat quality. So now I can look at a certain water year. I can look at all the water years here, and I can just count up how many days over that water year do the flows. So this is my range. That's my range right there. I want to know how many days in the year does the flow occur within that suitable range, right, for that life history stage. So in 2003, there were 94 days during the critical period of the year, that breeding period of the year, when we had suitable conditions, right? So that was 1 year. So now what I can do is I can start to incrementally decrease the flows in those 5% increments. And I can say, as I drop the flows in 5% increments, how many less days am I going to have where the flows are within those suitable conditions? And so then my risk is really just the ratio of how many days under this certain amount of alteration. So it's 70% of unimpaired flows, I only have 82 days compared to 94. And so that gives me a 13% risk. Really complicated math, right? Even a manager can understand that, right? So now I can create a risk number and I can take that and I can plot it. So now all I did here is I took all of the risk values of this 13%, and then as I stepped it down from 100 to 70, I can plot what that risk number is, right? So that's just for 1 year. So now I can do that for all of the years in my period of record, and I get a range that looks like that over all of the years. So now I have some sort of range, sort of a point cloud that shows me something about risk. And so again, in this case, I want to create a bracket curve. So we took the 80% again. Nothing magic about 80%, but we took the 80 percentile. That could have been the 50th percentile or the 100th percentile. And that becomes my risk curve. So now I have a way of relating percent of unimpaired flow to this ecological risk, which is really just how many less days in the year are you going to be able to support that species over the period of record. So what I showed you there was for one species. Now I can do that for a bunch of species, right? Because I've got salmonids and I've got other species, so I can do that for a bunch of species. So each of these curves represents that same analysis for different species of concern. And then here I just took the bracket curve. This is the umbrella curve that encompasses all of the species of concern. So now if I manage based on this curve, I know I'm being protective of all of the other species whose curves are underneath them, right? And so that's for one site in the watershed. And so now I can apply that same type of risk approach that I showed you before, and I can start to create these zones, right, that a manager can use. So I can say, and I can put numbers on it. So I can put numbers on it and say, the percent of flow, POF percent of flow, if I'm in between 85 and 95% of that flow, I'll be in that sort of good or moderate to low risk. And again, a manager can decide which risk category they want to be in. So the last piece of this is for one site. Now we do this for a bunch of sites over the region. This is in the Eel River watershed up in Northern California. And so this is the exact same thing, but now all I've done is I've done it for a bunch of sites and I've created these integrated curves. And it turns out, not surprisingly, that they tend to group by drainage area. And so we have different curves based on the drainage area of the basin that goes into that particular area. So now I have these regionally protective curves. I can create those same risk categories. And then it depends, again, not surprisingly, if you're in a big catchment, you have more risk, so more buffer in the watershed, it can tolerate more of a deviation. And as I step down to these really small catchments, then they're much more sensitive to the flow alteration. So again, it doesn't give a manager an answer, but it gives them the tools that they can use to hopefully make a decision and defend the rationale behind that decision. And I'm going to tell you, when I briefed the head of the Division of Water Rights, he was not happy about this, right? Because he's like, I need a number. I'm like, it's not my job to give you a number. That's a policy decision. That's not a science decision, right? So that's up to you to decide where you're going to pick. But then we can apply this across a watershed, and so not too far, and then we can start to map out different parts of the watershed based on the catchments, and we can start to give the users, which are the diverters, in this case, the cannabis growers, they can start to look at this and get some predictability on which parts of the watershed are going to be able to sustain more or less diversion. So when they go in to submit their permit applications for diversions, they have a sense of kind of where they are in the landscape and how much likelihood they are to be able to divert the water that they need to support the grow operations. So that's kind of about as far as we've gotten. So there's lots of unanswered questions. So we've got a toolbox of methods, right? But as I hopefully impress upon you, there's a lot of decisions along the way that have to be made. 80%, 50%, thresholds, all that. And so right now we're doing a bunch of sensitivity analysis to try to understand kind of what are the implications of those. We sort of got the workflow worked out. People sort of understand how we're doing it. Now we have a lot of sensitivity analysis to do because we really want to understand how important are some of those decisions in terms of, how it affects the ultimate risk curve. We also are still talking about how do you put it all together. I showed you 3 different ways of doing it. Do you take the most conservative answer? Do you take a median approach? Does it vary by season? Does it vary by type of watershed you're in, or upper or lower? So there's lots of additional things to explore in terms of how you take the different tools in the toolbox and figure out when there is the most appropriate way to use them in combination with each other. So, and then the last thing is there's a lot of uncertainty. These are models on top of models on top of models. So, how do you quantify how that uncertainty propagates through the whole workflow is another thing that needs to kind of be fleshed out as well. So there's still some, we have sort of a good foundation to work from, but there's obviously a lot of pieces that still need to move forward. The state ultimately wants to set flow criteria for different regions using these tools, so we're continuing to work through some of those. So my last slide. It's kind of like all good science, right? Answers beget questions. And so the next thing that we're working on, I get this question all the time, is water temperature, right? Turns out, as you guys all know, temperature is really important. The temperature and flow are tightly coupled. And so we're starting to do an analogous set of analysis with temperature and see how we can sort of better understand the relationships between flow and temperature. When does flow become the real determining factor versus temperature being the determining factor? Some of you may recognize that picture. We have other uses of these systems. And so we're starting to work with some social scientists to help us understand how do you quantify the sort of risks and values of the non-ecological usage, right? Because ultimately, if you're a water resource manager, you have to be able to quantify the trade-offs between the ecological piece and the other human, which are very important and drive a lot of policy decisions. So working with our social science partners to kind of figure out those trade-off analysis tools, which to me is super interesting because they use a whole different set of tools than we use, which is always interesting because there's obviously some cross-pollination opportunities, right, with different types of modeling approaches. So in California, we have 500 distinct estuaries along the coast. Most of them are at the mouths of these river basins, right? A lot of river mouth estuaries. And we've really done very little work to understand how these changes in watershed-based flow management, how they propagate into the estuaries, and what does that mean for the ecology of these estuaries, particularly because many of our estuaries are seasonally closing to the tides, the bar-billed estuaries. So there's a lot of work that needs to be done to understand that coupling between modification of watershed hydrology and ecological effects in the estuaries. And then we have an engineering department at SWRP where I work, and they're starting to look at a lot of different nature-based solutions. This is some work we did with one of the sanitation districts looking at green roofs and green walls and hypereic exchange for temperature modulation, and like, can we start to get some innovative strategies to begin sort of managing these effects. So those are all sort of areas of future work that we're continuing to explore. And with that, I'll go back to my key takeaway. So hopefully I've convinced you over the time that I've been up here. It's a very complicated environment, highly variable. So we need lots of tools. We like the risk-based approach because it gives us a way to sort of manage a lot of the uncertainty and understand that there are no bright line answers, right? And that you have to ultimately make a policy decision. And that working with our partners through the co-development process has been really critical because this is it's a fairly complicated workflow and process. And I presented it in a very linear manner, but I think all of you probably appreciate this was a very non-linear process to get to this place, and lots of iteration back and forth to kind of will continue to evolve, I'm sure, over time as we continue to work. So with that.
All right, round of applause for Dr. Stein. So we actually do have some life on YouTube, including a question from someone you're going to go eat lunch with in a moment. So Matt Cohen asks, what is the feedback loop to the users? So basically, how do you assess if the management decision support worked? Is it compliance? Is it voluntary?
Yeah,
I'm coming to you, students. So think about your question next.
Yeah. So the question is, so what's the feedback and how do we know if it worked? So I would say there's two levels. So one, first of all, does it work? Is there uptake by the user community? And so at that level, there is uptake. I showed you a couple of examples, and we're starting to see uptake from the user community in terms of applying these methods into sort of a policy or management. The bigger question in terms of how it worked is what I would sort of call more of a validation, which is if you implement these methods, does it manifest to the expected biological manifestation in the field, right? And that we really don't have good answers to yet. We had some inklings with the bioassessment because we do a lot of bioassessment, so we're able to go back and do some retrospective analysis in some of these areas and get some insight. And we have some initial suggestions that the bioassessment communities are responding in the predicted ways to flow management. For some of the higher trophic levels, it's sort of TBD. One of the things that's interesting, because we do so much treated wastewater reuse now, we actually have the opportunity with some of our wastewater agencies that are using these, where they can actually manipulate the flows as they, based on the reuse practices, and we can start to track the responses in the biological community. So the bottom line answer is we don't know. But we actually are in a position to begin to start testing that, and hopefully iterate and refine over
Come
time.
back in 5 years and let us know.
Exactly.
Yeah, and if you have to go to class, great, otherwise stick around. Questions from the room, from students especially. But also graduates. So yeah.
Yeah, all
Go
right.
ahead, Paul.
Well then, yeah, that was a great talk. I really liked the part where you were talking about sort of separating the hydrographs and looking at different things there. And I was sort of wondering about like the amount of data that you need to sort of construct those hydrographs, and like obviously different years are going to have different conditions, but yeah, and like how uncertain the uncertainty there I think is.
Yeah, so the question about how much data to construct the hydrograph. So I didn't talk about it here, but a few years back, when we started this, we mined all of the gauge data in the state, and we basically did we did a hydrologic classification of the state. So we broke the state into sort of we broke the hydrographs into different hydrograph archetypes. So like, for example, we have a hydrograph that reflects snowmelt dominated systems, or one that reflects groundwater dominated systems, right? And then we created what's called the dimensionless reference hydrograph. So, and that represents sort of a manifestation of what an annual hydrograph in that type of system should look like. And it's got a range. So it's basically looking at the median and the 25th, 75th, 5th, and 95th percentile. So we can create this dimensionless reference hydrograph for these different hydrologic classes. And that allows us to sort of bound what we think over time, that range of uncertainty. And for things particularly like in the wet season, we have these huge ranges, right? Because it's a highly variable system. So when we do these things, we're usually working in practice. When we do those functional flow metrics, we work usually within the interquartile range. Right, and so we're usually looking at like those boxes, those colored boxes I showed you. We're usually bounding those by the 25th and 75th percentile of those expected ranges.
Cool.
So it can be a fairly broad
Sure.
range.
Go ahead, Patrick, and then Nick.
I'm kind of building off that in terms of like how confident are you in your assessment of like these different kind of risk categorizations, like across different watersheds? Does your confidence kind of vary depending on like rainfall variability? And how much data you might have on like indicator species in these bio assessment, all that information that goes in.
Yes to all of the above, right?
Yeah.
So our confidence, right, as you probably saw, there's lots of pieces that go into this. And so that's why I talked a little bit about the uncertainty analysis. So there's, like you said, exactly what you said, the confidence in our hydrologic predictions, the confidence in those habitat suitability curves. In this case, most of the work I showed you there was done in the north coast of the state, because we actually have a lot of data, because that's where most of our salmon species are. And in that case, we have like those habitat suitability curves, the kind of hypothetical or the conceptualized one I showed you. We had maybe over a dozen curves, right? And we actually did a lot where we took out the outliers, and we kind of tried to get sort of a more kind of median type of curve. But for other species in other parts of the state, you might only have one version of that curve, right? In which case you have much more uncertainty associated with that. So there is a lot of uncertainty that propagates through this analysis, and that we're trying to sort of manage that uncertainty. But for sure, things like sensitivity analysis and being transparent on those sources of uncertainty is important, right? Because we're embedding a lot of that uncertainty through the workflow right here. So.
Let's have one more from Nick, and then of course stick around if you'd like to ask another question.
Hey, yeah, I really like the talk. I think it was step 2 of the flow chart. It was one of the models, it was one of the random forest models where we were linking the bioassessment scores
Right,
to the feature importance of.
The
I was just wondering if you'd clarify that model, and what you were linking each one of the species to.
in
for-
was it the
Yeah.
one for the part 3, those,
Some of them part
In
2.
part 2.
with the bugs?
Yes.
Yeah.
Yep, it was like each one of the bars, the feature importance had like a bug above it. I was just wondering how you were linking.
Oh,
each
I
of
know,
the
I know what you're talking
species.
about. Is it,
It's roll performance.
yeah, this
Yep.
one,
Yeah.
yeah.
I was a little confused about
Okay.
this model.
Yeah, so this is just a boost regression tree analysis. So what we're doing here is we're basically, way this, which is basically just a glorified classification regression tree, right? And so all we're doing here is we're taking we're taking the hydrologic data we have over the period record. And we're looking at the bioassessment source. So we pair a bioassessment site with a hydrologic site. Usually, we snap it to the closest gauge, right? And then we're just going through the sort of the classification process to say, as you change each one of those flow metrics, what is the associated sort of response in the biological community? And where is that response more tightly coupled? And so you basically are going through sort of a classification tree, right, which we said the most important variable, in this case, 10-year flood duration caused the biggest bifurcation in the bug community, when we varied the 10-year. And then as we step down through the classification or tree, we're saying 10-year flood duration was the most important. What was the next most? So the next bifurcation in the tree would be 7-day minimum timing. So if you look at the output, you get basically like a tree, like a regression tree. That's the output. And that allows us to rank the flow variables based in terms of which ones are the most important in terms of causing that break in the community between sort of good and bad, right?
Okay, and so for the first bug there with the 5 hydrologic variables that you found important, why are there only 2 for the second?
Oh, I did, yeah, I went through this pretty
Uh-huh,
quick.
yeah.
So the algae, these three also were for the algae, but we added in. So the algae, because we analyzed them separately, we analyzed the bug data separately from the algae
The
data.
green thing is algae, not like a larval case of
Yeah.
an insect or something.
Yeah, so this is, sorry,
Yeah.
I'm sorry, this is the algae, right?
Yeah.
So these in the box, these 3 were the most important for the
Benthic
bug-
macroinvertebrates.
the benthic macroinvertebrates. And then these 2 were not important for the benthic macroinvertebrates, but they were important for the algae.
Yeah.
Gotcha.
Yeah.
Okay.
So you can do it by functional group, you could do it by species, you
Right.
could do it by whatever,
Right,
any.
yeah, I went through that pretty quickly, so when we did it with the CSCI, the California, the benthic index, we had a set of hydrologic variables that were the most important. But then we came back and did a second analysis with the algae, that mainly diatoms, and we had different hydrologic variables that were responsive in the algal community.
Okay.
Yeah, so it's 2 different analyses, so I should have probably showed these as 2 separate plots, but I just kind of.
Thank you.
Well, let's thank Dr. Stein one more time. Thanks. All right, so for students, we have, I guess, one more write-up to do. This is our last seminar of the semester. I think I'm basically caught up except for last week, so please email with any questions about your abstract rating, and we will see you next semester. Come on back. Thanks,
If you have
everyone.
any outstanding abstracts, make sure they're in before the 3rd, which is the last day of classes.
That's right. I'm sure they're all outstanding, but if they're, yeah.
Well,
Unsubmitted, yeah.
rephrase that perhaps.
Yeah. Thanks.